I'm Tim Ventura, and we're joined today by Dr. John Parmentola, an adjunct staff member at the RAND Corporation, where he works on defense, energy, science, and technology strategy and planning. His career also includes experience as Senior Vice President at General Atomics, the Director for Research and Laboratory Management for the U.S. Army, Chief Scientist at the U.S. Department of Energy, and Chief of Advanced Systems and Operations at the Defense Threat Reduction Agency. John is an honorary member of the U.S. Army S&Ts, a fellow of the American Association for the Advancement of Science, and a recipient of the Presidential Rank Award for Meritorious Executives, along with the U.S. Army's 10 Greatest Inventions Award, the Alfred Raymond Prize, and the Sigma Psi Research Award, among many other awards and honors. Dr. Parmentola has a PhD in physics from MIT and has served on the faculty of MIT, West Virginia University, and as a fellow at the John F. Kennedy School of Government. So, John, welcome back, sir. And in case I forgot before, thank you for your many, many, many years of federal service. Thank you so much for serving, sir.
Thank you.
So,
Thank you, Tim.
Absolutely. Today, we're talking about your research into Milankovitch theory, which is a concept developed by Serbian scientist Milutin Milankovitch that proposes that long-term variations in the Earth's orbital cycles are responsible for Ice Age climate periods. So let me start out by asking if you can help us understand this from kind of a high-level bird's eye perspective.
Yeah, well, the simplest way that I can explain it is there is a quantity that's measured with satellites called the albedo. And the albedo has to do with the amount of sunlight that's reflected back out to through the atmosphere, back out to space. And if the albedo change right now, the estimate is about 30%. You know, I don't know how accurate those measurements are, but these have been made over, 40 years, so 30, 40 years by satellites. And it's unknown how much the albedo has to change things on Earth. But as you can imagine, as more sunlight is reflected out, there's less that's retained, and that can cause a temperature drop. So the temperature drop results in more cold air. And that cold air, additional cold air, can mix with warm air to produce snow and ice. And so as the snow and ice accumulate, the albedo goes up. There's more reflected, there's more cold air created, and more air mixes with cold air mixes with warm air to produce more snow and ice. And this keeps on going until there's no moisture left in the air, or very little.
Okay.
So you wind up with a desert. Most people don't realize that Antarctica is a desert because there's very little moisture in the air there. So, so now you ask yourself, well, if the albedo changes, where is it likely to change? So 65% of the landmass is in the northern hemisphere. So if snow and ice are going to accumulate, they're going to accumulate in the northern hemisphere. So what Milankovitch speculated was that because the sun's rays do not reach the North Pole or in the vicinity of the North Pole, that's a likely place where snow and ice will start to accumulate. And he focused on the tip of Greenland, which is at about 65 degrees north latitude. So if you think about it a little bit, the Earth while it goes around the sun, rocks. So it's like rocking in your chair, right? It has an axis of rotation, but then it can rock back and forth.
Yeah.
This is the called the obliquity. Okay, it's the angle that the spin axis of the Earth makes with the orbital plane, and it can vary. Now, the variation isn't very large. It's only about 2.4 degrees latitude. Now, if you translate that into miles on the surface of the Earth, it's about 140 miles.
Okay.
So now, if you think about it, the sun rays hit the Earth, right? And the rays make an angle with the vertical, right? Because if I look out, directly out along a radius of the Earth, the sun's rays make an angle with that direction. But if the obliquity gets smaller, in other words, decreases, there's more exposure in the north. And so some of those rays begin to have an effect on what's going on in the northern latitude. Similarly, if the obliquity angle gets larger, there are less rays that hit the north, right? So he speculated that what happens is because of the obliquity, the sun's rays are compromised in terms of reaching the north. That reduces the amount of snow melt there. And then you say during the summer solstice, right? The summer solstice is when the Earth axis of spin is pointing towards the sun. So this past summer during June, the Earth was at aphelion, which is the furthest distance from the sun in its orbit. But the axis was pointing towards the sun. And if the obliquity angle is larger, right? Less sunlight is going to get up there in the north. So there's less melting. You fast forward to the winter solstice, you have the opposite effect, but the nights are very long.
Yeah.
And if there's interaction between the cold air and the warm air, there'll be snow deposited. So there's a differential in the amount of snow that accumulates between the summer solstice and the winter solstice. And this accumulates over time.
Okay.
So now if you imagine every year there's an incremental amount of snow and ice that accumulates up north. Let's say it's 1 foot, right? And it keeps on doing that. Well, after 10,000 years, you got 10,000 years of ice and snow accumulation, and you're in a very, very cold climate.
Yeah. Yeah.
Okay, so he attributed it to the obliquity.
Okay.
And, my work,
and you got into the wave aspect of this, but John, before we do that,
yeah,
let me do a screen share. I have a page from NASA. I just want to help people visualize this a little bit more effectively. Okay, so video number 1 is changes in eccentricity.
yeah. Now, let me point out, okay, as you're doing that, right?
Yeah, absolutely.
So if you think about a point on the Earth's surface, right? At one point on the left side, it's closer to the sun. And then as it expands, it's further away. So if I were looking at a point on the Earth's surface, I would see the sunlight diminish on the right side, right? So it oscillates between intense and less intense, right? Back and forth,
Yeah.
back and forth. Well, what is that like? That's like a wave, okay? It has
Yeah.
a peak and then it has a trough. It has a peak and a trough, a
So
peak and a trough.
this
So,
is our orbit. This is our orbit. And
yeah,
I got two more of these also. And I
right.
think that'll
That's,
reinforce your point. Let me go to the next one.
yeah, now you're talking about the obliquity. This is like rocking in a chair, right?
Yeah,
So,
you mentioned that earlier.
yeah, so this is like rocking in a chair, so if it points towards that axis, that blue axis there, points towards the sun at a high angle, right? A large angle, uh, the north gets intense sunlight,
Yeah.
right? More intense sunlight. For rocks the other way, it gets less, right? So right now, the angle is about 23.4 degrees, I think, which aligns the sun's rays, not with the equator. It aligns them with the Tropic of Cancer or the Tropic of Capricorn in the
Okay.
southern hemisphere. So that's where the rays are most effective in terms of impinging on the Earth.
Yeah.
Okay?
Yeah.
But as you go north or you go south, the rays make an angle, and so only a fraction of that sunlight really effectively gets into the Earth's atmosphere and gets possibly absorbed or reflected.
Yeah. So that's our tilt. Let me go to our last one here.
Yeah, this is called a precession. So the precession is similar to what happens to a spinning top. If you ever spun a top as a kid, the axis doesn't remain fixed, right? It precesses around an imaginary axis that's, vertical, right? So this affects how the Earth points in direction. So this can affect the uh, area of the Earth that may receive more intense radiation or less intense radiation, depending on where it is on the Earth's orbit, right?
So what's interesting is, and you'd mentioned this to me before the interview, you've got these three factors that work together. And again, those are, let me see,
The obliquity, the precession,
precession
and
and
the
the
eccentricity.
eccentricity. Yeah, I wrote those down so I remember
Yeah,
them.
yeah,
So you've got those three that work together. And then you mentioned this before the interview, you've got other factors as well. And all of these work together. Uh, for instance, the gravitational pull of Jupiter, gravitational influence of other planets have these tiny, minute influences. You'd said that there are a couple of scientists who have worked on this. Their models include over 300 different variables. And basically, when you add these all together, they turn into what you've been working on, which is kind of a wave function for what they call insolation. And
yeah,
insolation is the amount of sunlight, basically sunlight per square meter on the ground.
yeah. One way to think about it is this, right? So the sun's rays come a very long distance and they approach the Earth and they're all in the same direction, the rays are impinging on the Earth.
Yeah.
But one way to think about it is that the Earth's motion is beating on what's called the solar irradiance. It's beating on it, right? And the way it beats on it is with the rocking the distance closer or further away. These are cyclical motions. They're cyclical that beat on it, and in beating on it, the sun's rays get distributed on the Earth's surface. And so depending upon the particular time, the distribution of the sun rays on the Earth's surface have different intensities. Okay, so at one time, at one point on the Earth, it may be high intensity. Another time, it might be much lower because of this beating, right?
Yeah.
And so, what I'm describing is essentially a wave phenomenon. It's like an amplitude modulated radio wave that you listen to on your radio. It's amplitude modulated in time. The insolation is an amplitude modulated wave in time. But one important point is, as a wave, it's constructed out of these basic motions that the Earth exhibits. So each one of those produces a wave that then add up.
Yeah. Now, let me stop you again just for a moment. And I'm going to share. Let me see if I can get this correct. So this is your article for everyone to take a look at that, and I will put a link in the interview as well. What is Milankovitch theory? What is it not? And what can we learn from it? And the reason I wanted to show this to people was you've got some graphs in here. Now you were talking about the wave cycle. This is kind of an example of it. It's like a sine wave, kind of.
Well, these graphs, what they basically show is that these three parameters, eccentricity, precession, and obliquity, are cyclical, but they're not periodic.
Yeah, so they're not regular. They're
not
come
regular.
and go.
No,
So it's not like a sine
correct.
wave. A sine wave is regular. These are, and what's interesting is, as a wave phenomena, because each one of these represents maximum and minimum sunlight, you would combine all of these and normalize them, and then it forms a very confusing waveform.
Yeah, it becomes a rather complicated looking wave, which if you think of a sound wave, high pressure, low pressure, and so on, which is kind of similar. It has a beat structure to it. In other words, high points and low points, and everywhere in between. So if you think of a sound, it would go to high intensity sound, low intensity sound, and it could be a very complicated pattern of a sound wave. Similar type of thing happens with the insolation. What these graphs point out is that the waves produced by these individual cyclical motions are not regular. They're what people call aperiodic or quasi-periodic functions. So you go down a little bit, and up. Sorry, go up a little bit.
Actually, the sum of waves from the deconvolution model, I thought that would be probably perfect.
Yeah. So what you're looking at right there, that's the insolation. That's what it looks like as a function of time. So it's a very complicated wave.
And this is the addition of all three of those other waves.
Right.
This is,
but the most important point, you see, in the work I've done, I tried to use physics to help me understand what the major contribution in terms of waves contributes to the insolation. So you might say, well, there's three, right? Well, I've reduced it down to two important ones. And one of them is very important. and the other one is much less important.
Yeah.
Okay, so I actually wind up contradicting Milankovitch because the obliquity is not a major contributor as much as another wave. And in order to understand this, you have to combine two motions. One is the eccentricity and the other is the precession.
Okay.
Okay. And so remember what I said. If I'm at perihelion close to the sun, right, and the axis is pointing towards the sun, it's a maximum, right? You get maximum insolation. Those are the peaks that you see here. And then when the Earth, the precession axis rotates around, right? But that occurs on average every 10,000 years. 10,000 years later, the Earth is at aphelion, furthest away, with the axis pointing towards the sun. Those are the minimum that are occurring here. Okay, so the combination of the precession and the eccentricity dominate that particular feature of the insolation. And so here what you've displayed are the waveforms that contribute to that insolation. Okay, and so the red line, the red curve, that's the obliquity. Okay, that's the rocking back and forth, right? As I said, it's only 2.4 degrees. It's only 2.4 degrees. It's very slow. Its average cycle is 40,000 years. Okay, and so it tends to have a slow, low amplitude effect. And then you see these other ones. That's what is called, in the literature, is called the precession index.
Okay.
Okay. That's a combination of the precession and the eccentricity. Okay. And what I've been able to do in a model is to tease that out so you can see how it compares with the obliquity. Okay. The gray curve, you know, which you can barely see, that's the sum of them. Okay.
Yeah.
That's the sum. So the precession index dominates the insolation. And what I show in the paper is the interglacials. You can see right here, the top graph is a model representation of paleoclimate data taken from ice cores in Antarctica and put into a temperature scale.
Yeah. Now, John, if I could jump in again for the audience, because this was something I learned when I was studying this. So technically, we are still in an ice age. That was kind of a surprise. We're in what's called an interglacial period. So you have
Right,
glacial
that's off to
periods
the
and
right.
interglacials.
That's we're in the piece right there off to the right. Okay, in the graph. We came out of the glacial about 17,000 years ago, 18,000 years ago. That's where the bottom is. And then it rose up, and now we're in that part that's up there that looks very narrow on the right side of the graph. So, and you see other interglacials here, you know, and the issue is there a relationship between the behavior of the insolation and the creation of an interglacial? In other words, a steep rise from the bottom to the top, and then a termination, which means a decline. is there some kind of relationship between them, right? You know, the problem you have is if you count up the number of interglacials that you have here, you you have roughly about 13, you know, if you want to count them. But the number of transitions in insolation from minimum to maximum over 800,000 years, because that's the scale you're showing here, is 74. There's 74 such transitions. So how do those transitions line up with this?
It's very, very complex.
Yeah,
It's very, very complex.
So you have to be looking at some subset of effects that somehow coincide with these creations, right? Now, what I show in the bottom graph is the precession index wave. And what you can see from that is a rough alignment between these interglacial and glacial periods with increases and decreases in the amplitude of the precession index, right? Going back, I said the precession index dominates. Well, now you're seeing this domination. It coincides with temperature trends that you see, right? And you can almost, you know, follow these things as you go along by looking at this rise and fall of the precession index, right? And so that gives you some indication as to how the precession index affects the creation and termination. So for example, you know, if you look, I don't know, I can't see it right now. There's a, you know, a spike, I think it's 7C. You can see the rise and the fall, you know, and so on. What's happening fundamentally is there's certain times when the obliquity wave and the precession index synchronize. They synchronize, they reinforce each other.
Yeah.
Either in a way in which the synchronization is such that the insolation increases, or they synchronize in which the insolation decreases.
So
those
one
synchronizations, which are the rare occurrence, is how interglacials are created and terminated.
Okay.
So it's a synchronization phenomena that occurs. It's relatively rare. That's the reason why the number of interglacials is rare.
Now, one of the things that's interesting is you have, because of the wave theory and because the detailed work that you've done on this, you've been able to come up with better estimates or more precise estimates, and they're slightly different as well. I did some research on this. I believe NASA.gov, their ballpark estimate is about 50,000 years until the next glacial period, right? Because again, we're still in the Ice Age, but the next glacial period, they estimated 50,000 years. There is a scientist down in Texas, I believe. He did estimates that said, well, we're actually overdue for the next Ice Age. You are saying it's about 500 years for the next glacial period.
It's within the next 500 years. And if you could put up that graph with the
absolutely
temperature graph, I want to point out one thing. Just go up a little bit.
Okay.
I'll talk about that maybe later. But yeah, so if you look at this temperature graph that's inferred from the paleoclimate data, look at the interglacial to the left. Okay? And then look at the one we're on now to the right. Okay? Now look below. You see the behavior of the precession index in terms of the rise of the peaks and the fall, right?
Yeah.
Look over to the right. Rise of the peaks and the fall. There's a similar type of behavior. Now, if you look at the interglacial on the left and you analyze it, It's very similar in terms of its behavior of its obliquity, precession, and eccentricity as the one we're on now, okay, which is called the holocene, right? So these two interglacials, the one on the left and the one on the right, have very similar characteristics. So now if you go to that graph that the two graphs below, that one right there, here's a comparison of the insolation. The vertical line in both is where well, the vertical line on the left is at 0, which is today. Okay, that's the vertical line. The black curve is the insolation that's coming down, decreasing, and forming a minimum. This is where this synchronization is occurring, right at this minimum. Right? The one to the right is the one that occurred 787,000 years ago, and it has a very similar type of behavior, right? So now if you look at the scale on the left, it goes from 0 to 1,000 years. So that minimum is a very shallow minimum. It's very, very shallow. The best you can do is estimate it that within 500 years, there'll be a termination, similar to the one that's on the right, okay, because that one did terminate, okay, and it terminated near or close to that minimum. But it's very difficult to be precise in all of this.
Because there's so many variables involved.
Yeah, there's variables, and you're relying on data that has errors in it, and some of those errors are unknown. They're estimates. They're not.
John, if it's okay, I wanted to ask you also, and I hope I'm not taking this off topic, but when I was doing research for this, I wanted to ask about the thermohaline circulation, which is also called the global ocean conveyor belt. This is also involved glaciation, right? Because it takes heat from the equator to the polar regions. Is this involved, or is that a minor variable for what you're studying?
Well, it's hard to say, okay, because the reason why I call my estimate speculative is because the insolation is only part of the story. What Milankovitch's theory really does is it imposes certain insolation conditions on the Earth's complex climate system, right? The issue is, how does that system respond specifically to those conditions? What is the specific mechanism, climate mechanism, that causes the Earth to go into a temperature descent, right? This is unknown. We don't know it. Why? Because we don't understand the Earth's climate well enough. Now, if you look at the poles, people talk about extreme weather.
Yeah.
Okay. Well, the most extreme weather on the planet is at the poles. Each pole has a huge, huge cyclone, each the size of Asia, of cold, dense air that's circulating counterclockwise. And that counterclockwise circulation is caused by the Coriolis force. It's the same force that causes hurricanes and cyclones, okay? But in the North Pole and the South Pole, you have huge amounts of very cold, dense air. The thing that keeps them up there is the jet stream. The jet stream holds it in place so it doesn't move significantly south. Okay, because if it does, during certain times of the year, there are huge temperature gradients where warm air wants to go, or even if you want, warm water wants to go north, right? But warm air mixing with cold air causes what? Snow and ice.
Yeah.
So the issue becomes one of spillage of these cold regions down south where they mix. Now, are there examples of this? Sure. In recent years, people have been very concerned about the polar vortex events. These have reached all the way down to Texas, as you recall, right? Texas, they had this cold vortex event that affected their energy generating systems, both wind and gas, right? Causes incredible problem. I mean, people were freezing to death, not knowing what they were going to survive. Okay, scared that living daylights out.
Yeah, yeah, because
Okay,
it strains
these
those
events,
systems. Yeah.
these events happen, but the problem is we don't understand in detail how they occur, and we can't predict right now when they occur. But it's events like that which can increase the amount of snow and ice to accumulate and change the albedo. Okay, now, if you look at the insolation over the last 11,000 years, it peaked 11,000 years ago, approximately 11,000 years. It reached a peak in the north. Okay. It then gradually came down to where it is today. And that decline is about 50 watts per square meter. Okay? Well, if you think about it, if there's that much less insulation shining up in that region, right, over that period, it's likely to increase the amount of cold air that's there. In other words, this cold air region may have grown in some way. But in order for it to mix with warm air, it has to go unstable. In other words, it loses its vorticity. Its circulation gets broken up
Yeah.
to
Yeah.
maybe smaller cyclones, and then you start getting this spillage that goes south, and then you get increased snow and ice. That mechanism is not understood. It's an area of research that we don't understand.
Well,
But we should understand it, but we don't. So it gets back to this question: how does the insulation couple to the Earth's climate system, and how does it affect it? I just don't know. I mean,
I think it's really valuable to showcase this to the audience, though, because it helps them to understand the complexity of climate models. And I think it also helps them to understand why, for instance, NOAA and NASA, when they do climate modeling, they've got massive supercomputers involved with that. And now I think people may understand a little bit better why. I mean, again, the things that you're talking about, these are just a few of the variables. You're working with the major variables. You mentioned that some people have over 300 that they're modeling at once.
yeah,
So there's a lot going on here.
yeah. Well, we can look for patterns, right? And the patterns might suggest some things, but proving that they are the cause of something is a whole other matter. In
Yeah.
order to do that, you need a theory. Milankovitch theory isn't a theory, in my view, because it's not complete. In other words, it cannot by itself describe the behavior of the Earth's climate over hundreds and thousands of years. It lacks the completeness that's required in order for it to be a theory. In other words,
As
all
you
the
said,
principles and elements that go into a theory, and then translate that into mathematics, and then develop computational methods that are precise, that can take into account the most important effects and argue that certain effects are small, okay, that you can calculate them, but they're not going to make any difference. But you have to prove that. You just can't wave your hands around and say, okay, they don't matter,
well,
right?
and as you said with Milankovitch, it seems like what he has is a model that's imposing conditions on a complex system.
Yes.
And so you might almost look like that maybe it's like the guides on the side of a road, right? You have to stay inside of the lines on the side of the road. You have to stay inside the lines when you're driving, but
Yeah.
where you are inside the lines is due to many other things.
Yeah. Well,
So
I mean, that's a good analogy. I mean, um, I don't have definitive answers. What I do have is a bit of a better understanding of the role of these three parameters in affecting the insulation, and how that effect might manifest itself in the creation of interglacials, and then determination of them based upon unique conditions that occur amongst these three cyclical parameters that affect the insulation.
yeah,
And you can understand it a little bit, right? Because if you look at the precession, its average cycle is about 21,000 years, 21,000 years. That of the obliquity is 40,000. So one divides into the other. So you can imagine there's certain circumstances that may occur where they're synchronized, okay, in some way. And the eccentricity basically causes, because of changes in distance of the Earth from the sun, changes the intensity of the sun at the Earth's surface. So that's its role in this. So if the precession points in one direction, 10,000 years, it points in the opposite direction. But during that period, the eccentricity changed. And it changed significantly enough, that it had an impact on the Earth's climate. And the obliquity can enhance or diminish that effect depending upon timing. Okay. And so that's my view of how, at a more basic level, this type of phenomena could occur.
yeah. Well, John, on that note, let me thank you again so much for your time. And again, thank you for your many years of service.
Well, thank you, Tim. Thanks for the interview. I hope people have a better understanding of this. It's really very important, and
Yeah. And I'll link them to the article. And I think that this is an interesting area for people to do more research on their own. And I think that they'll definitely have to, because it's a very complicated
by the
topic.
way, I'd like to say one last thing.
Absolutely.
Even if, say, within the next 500 years, there's a temperature descent where more ice and snow accumulate up in the north, change the albedo, and we can actually see this and measure this, right? It's not a foregone conclusion that we will go into a glacial, a deep ice age. The reason why I say that is because there are simple ways of trying to prevent the ice and snow from accumulating. The way you do it is by putting energy absorbing materials on this ice and snow, sunlight absorbing materials that'll melt the snow and ice. Okay, so you could use carbon black, for example, and put it on the snow and ice. And that will cause more sunlight to be absorbed, and it'll cause the snow and ice to melt. This,
Yeah.
by the way, this is the way Ben Franklin, one of our founding fathers for our country, determined the temperature of color. He took handkerchiefs of different colors and he laid them in the snow. And from that, he could determine which ones were more absorbing of sunlight and which ones were less. And so he could associate the effectiveness of color in temperature. So this type of thing can be, we can save ourselves from an ice age. And I should point out that over the last 800,000 years, the Earth has spent 70% of its time, 70 of that 800,000, in colder temperatures, not warmer temperatures.
Yeah.
And cold kills, right? It's caused the extinction of species during these periods. And what animals do, and likely humans did, was to try and find warmer parts of the earth. And of course, the warmer parts are roughly 30 degrees north and 30 degrees south of the equator. The problem we have is we have, what, 8 billion people on this planet, and there isn't a lot of surface area to live on in that narrow band, you know, but with a bit of science, we can figure out how to combat this problem. And in fact, there's evidence that nature does this naturally, by the way. So when they analyze ice cores, they also find dust mixed in with the ice during certain periods over the last 800,000 years. So the speculation is that as one approaches the bottom of the temperature descent, the bottom of the glacial, there's so much vegetation and life that's been wiped out that that life turns to dust, and winds blow the dust around to cover the ice and snow.
Which then changes the albedo and begins to melt it.
Right, but what also happens is, remember the synchronization I talked about, the synchronization of these parameters, and they're coming together to drive the insolation up. That happens as well. So that causes the snow and ice to melt more rapidly. Both the dust and that synchronization contributes to the melting of the snow and ice. So that's how you come out of a glacial. So that dust is similar to what I described before. If you wanted to control the amount of snow and ice accumulation, you just sprinkle carbon on the snow and ice and allow the sun to do its job, namely melt it and try to control it. So we don't have to become victims of the next ice age. So,
John, on that note, thank you again, sir.
You're welcome. Thank you for the interview. I appreciate it. Love the questions. Really great. Thanks.